Okay, there we should be about now.
Got it.
Okay. So welcome to the first astronomical public meet at Santa Barbara Astronomical Unit.
Uh-oh.
Got it. Yeah.
Feedback.
Yep, got it.
There you go.
Okay, welcome to the first Friday meeting in August. This will be a complete Zoom meeting. We had earlier talked about possibly in person, but the COVID statistics do not give everybody a warm feeling. So we're going to stick for this meeting and for the foreseeable future, for the next few months, we're going to stick with Zoom only meetings. We have other Zoom events going on for us. This Monday, every Monday from 11 to 12, we have a question and answer period where we sit and chat among ourselves in the old radio station format, radio show format. You're welcome to tune in, watch it live, or watch it later. It's recorded on YouTube, as this meeting will be or is. And then on Tuesday night, we have the telescope workshop, which you can join live. Directions are on our webpage at sbau.org, not .com, but .org. That is not recorded, but you can check in live if you have questions you want to ask us about how to align your telescope, how to take the lens cap off, anything else, how to image. And I think that's, we're going to have a short comment on upcoming outreach from our outreach chairman, Chuck.
Okay. Is this the time for it?
Now is it, go.
Okay, well, let's see. Tomorrow night, Saturday, Kachuma Lake, telescopes in the Dust Bowl at Kachuma for the campers there. And then on Monday, for anybody who wants to risk their health and be in a packed room full of people, there's the Science Pub at Dargan's talking about asteroids. And then on Wednesday, we've got telescopes to Carpinteria State Beach. And then on Friday the 12th, Refugio State Beach. Saturday the 13th, second Saturday. So we'll be at the Museum of Natural History for the monthly star party. And we'll have our planning meeting before that at 6 p.m. I think the email said 6:30, but we're going to meet a little earlier because we're starting a little earlier. We're starting at 8. And then on the 19th, third Friday of the month, it's the Westmont Public Telescope Night. 20th, we're back at Kachuma. On the 24th, again, a Wednesday night, we'll be back at Carpinteria State Beach. Friday the 26th, we'll be out at Refugio State Beach. And on the 27th, we'll be back at Kachuma. And there's a couple of events that are still in process. I don't know if they're going to happen or not, but one would be bringing telescopes out to UCSB for the Associated Student Body. And one is at Sunstone Winery. So that's where outreach sits this month. Last month, we had 1,653 victims. So we're cruising along.
Did you mention next Saturday's star party?
Yes.
Okay. Okay.
8 o'clock.
And okay. The Baron, is there anything you want to add to that?
Only that our illustrious longtime treasurer, who's pictured on my screen wearing a wide brim hat, he and I are the only two with hats, is coming to meetings. You didn't make it last time I ran it for you, but Colin Taylor was there. Colin, wave at us so we all know you're indispensable and you're going to be part of this program tonight, we hope. It's good to have you on board. And Chrissy's in the middle of my screen. Hiya, darling. That's all I want to add until you introduce me.
Okay. Well, we're not going to do any more business tonight. The what is it, treasurer? We'll discuss that at the business meeting next Saturday, week from tomorrow. So right now, Baron, you can introduce our speaker. Take it away.
Okay, before we all meet future Dr. Claire, we like to help these young grad students on their way up, and when they're really big and running Griffith Observatory in the future, they'll remember us. Next month on the 3rd, I think, September 3rd, whether we're virtual again online or in Farrand Hall, Dr. Rocio Keeman, I believe is her name, will join our own Chrissy Cook, to update us on the web. You guys will probably have all kinds of new stuff to talk about, right, Chrissy? All right, we're looking forward to that. Now, Recent supersonic progress on the formation of the first structures in the universe. How do they know that? And we are going to ask questions. We hope we can at some point. She's a second-year grad student now at the Division of Astronomy and Astrophysics down at University of California at Los Angeles, studying theoretical astrophysics and cosmology with Professor Smadar Naos, looking into the formation of the first structures using analytical and numerical methods, meaning math. And she's a friend of the earlier UCLA grad student, Briley Lynn Lewis, who's talked to us a couple of times. I asked her, who do you know? And by golly, she gave us Claire Williams. Claire's in her house or home, or maybe you're at the university. Good evening. Welcome aboard. Hi.
Thanks so much. Yeah, I'm here at UCLA.
And you're going to be a doctor someday.
We hope.
Well, okay. Well, tell us what you've been studying and what you're going to talk about tonight. Curious.
Cool. I am, like you said, just finished my first year here at UCLA. I'm working with Smadar Naos on the formation of structure in the early universe. So I'm using simulations and analytical methods, so math, as you said, to try to understand how stuff forms at small scales in the universe. And that's what I'm going to be talking about tonight. So I'm excited.
Do you use graphics at all in your presentation?
Yeah.
Okay.
Hopefully this will suffice.
Sometimes
So yeah,
there's a big picture of the cosmos behind you sometimes.
yeah. Can I share my screen?
Please.
All right.
Assuming you can.
Hopefully it works. All right. Do you see that?
Yes.
There you go.
Great. Okay.
Thank you, Hal.
Let's make sure I can also see. All right. Yeah, I think I'll be able to pull up the chat. So if you put questions there, I should be able to see them, but you could also interrupt me. That will be good practice for my comprehensive exam. So cool. All right. Is it all right if I get started?
Sure.
Okay. So yeah, here's the title. I will be talking about recent supersonic progress on the formation of the first structures in the universe. I say supersonic progress kind of cheekily. Obviously, this has been the work of many years of my collaborators at the Supersonic Project. So Smadar, my advisor, and we have an international team that's working on this. So I list them on this slide as well. And yeah, I am just starting out. I know many of you are experts in astronomy, but I am anticipating, hopefully, that we'll have some people maybe watching on YouTube or watching the recording that don't know so much about astronomy. So I'm not going to assume prior knowledge about how physics or astronomy or how the universe works in this talk. So forgive me for re-explaining some basic concepts to you guys on the call. So yeah, let's begin. I wanted to start by contextualizing this whole ordeal with, of course, the big development that is revolutionizing the field, and that is JWST, the James Webb Space Telescope. And you will have a talk next month, apparently, about this. So that's very exciting. And you can hear all about the new data that is coming out. On the left, we have a beautiful artist depiction. And then on the right, we have the now famous first image from the telescope. I'm sure you were all watching the president's announcement of this one, just as I was. It's really exciting. But maybe, or a lot of people have been asking me who are not in the field, why did we have to go through all this trouble to make this enormous telescope so far away? That was such a risky maneuver. And so why do astronomers care so much to invest all this and create this telescope? So I wanted to go to the science objectives of JWST and point out two that are related to what I'm going to be talking about tonight. So this is just a screenshot from their website, the 4 central science goals of the telescope. And they all involve the formation and evolution of galaxies and structure in our universe. So the first science goal is early universe. They say that they're going to search for the first galaxies or luminous objects that formed after the Big Bang. And then the second objective is galaxies over time. So they're also planning to determine how galaxies evolved from their formation to the present. And so this is sort of the observational side of things. They had to build this telescope that can look really far into the distant past of the universe to look at this type of early, very old processes. So for those who don't know, the universe is expanding, and the further away objects are moving away from us very fast. And when objects move away from us, they the light that they emit gets shifted in color. So the wavelength gets stretched out and longer, which means it looks redder to us. So these galaxies that are emitting UV, ultraviolet, or visible light, the signal from those galaxies will get shifted to the infrared. And that's why this is an infrared observatory. The reason that we have to look at galaxies that's so far away is because the further away things in the universe are older. We're kind of looking back in time, because when we look out at a certain distance, the light from those objects had to travel across that whole distance. So if I look at something that's 1 billion light years away, the light had to travel for 1 billion years to get to me. So I'm looking at that object as it looked 1 billion years ago. But I guess people may wonder why we need to be looking at this stuff that's so small and so far away and so old, and why do we really even care about that? So my plan for today is to review how astronomers currently understand the formation of galaxies, what we think is happening, because before this, we didn't have a telescope that could look at these really early structures. And then I'm going to demonstrate that there are a few problems or tensions or anomalies with this theory. Then I'm going to introduce a new effect, a supersonic velocity, that was previously ignored in the theory, and then hopefully convince you that this supersonic velocity creates anomalous structures at small scales that could help to solve some of these current tensions with our theory. So that's the plan for tonight. And again, feel free to ask questions. I'm going to start with the first bullet point. So what is our current understanding of how galaxies form? If you are not familiar with this process, I'm going to give kind of a cartoon version of it tonight. So galaxies form out of the ingredients that the universe is made up of. And as far as we know, there are just a few things necessary to create our whole universe. So the first thing is obvious, I guess, the ordinary matter, the stuff that you and I are made of, like protons and electrons, and also radiation, I mean light in this context. But it turns out that normal expected stuff only makes up about 5% of our whole universe. And the rest of it is these two kind of strange components that you wouldn't necessarily have thought. So first is dark matter. There's a lot of evidence that there is a huge amount of this strange type of matter out in the universe. This is particles or something that has mass, but it does not interact with light, so we can't see it. Therefore, it is dark matter. The current best theories say that it is cold dark matter, and all we mean by that as astronomers is that the dark matter is moving slow relative to the speed of light, so it's not highly relativistic. So we call that CDM. And then the last component, so the dark matter is roughly a quarter of the universe, and the entire rest of the 70% or so seems to be this other very strange unknown component called dark energy. And we're going to focus less on that here because it's not quite as relevant to the processes, but what it's doing is causing the expansion of the universe to accelerate. And we call it lambda, which is that triangle Greek symbol. The reason it's called that is because that's just the constant that does that expansion in some of Einstein's equations. So together, this cosmology of our universe is called lambda CDM, and it seems like it's generally the best theory that we have that describes most of the observations out there. So now I'm going to describe how these ingredients, especially ordinary matter and dark matter, come together to form galaxies. So first, as you may have heard, the universe began with a bang. Maybe most, to me, the most easily understandable evidence of this happening is the fact that we observe galaxies to be moving further away from each other everywhere in the universe, which means that they all must have been closer together in the past. And so if you imagine rewinding the tape of the universe backward, you would see everything coming together into a very small space. And if you compressed all of the matter of the universe into a very, very small volume, you would get a big bang, right? A hot, dense, fiery plasma, a big fireball. And that's in essence what the Big Bang is. It's when back almost 14 billion years ago, when everything in the universe was compressed into a very small space. So this is a figure from the WMAP collaboration that kind of shows the history of the universe as we understand it. We have here, can you see my cursor? Yeah. So over here we have the current local universe as we see it, and then going further and further back in time, we get to this moment of the Big Bang. And actually, physics gives us a very precise understanding of those very first moments. So just using the tools of physics that are available to us on Earth and some observations of the universe, we can very accurately describe the first few early times of the universe. This is, I guess, a long period on a human lifetime, but in the course of the universe, it's not very long, but we know it very precisely. So this chart, many of these words may not mean anything to you, but I just am pointing out this time column, right? We know very, very precisely exactly what happened for the first few seconds, minutes, and 100,000 years of the universe. This is in part because we can reach these high energies in particle accelerators on the Earth today. So our particle accelerator experiments allow us to understand what was happening in the very beginning of time, which is really cool to me. And then the important event here is this time called recombination. And that's the big physics word that you're going to have to know for this talk. All it is referring to is a time when the universe went from this hot, dense plasma that was totally opaque to being transparent to light. So before recombination, you can't observe the universe before then because it was totally opaque and you can't see anything. But after recombination, the physical process that happened was electrons combining with protons to form hydrogen atoms, and the universe became transparent, so then we can see it. And so that's a very important event in the history of our universe. But after recombination, everything gets a lot more complex. It's not so simple as this precise particle physics measurements. So here's another picture of that, right? Everything that we were just talking about in the Big Bang happened in the very first moments of the universe. And in the entire time since then, we've gone from this very smooth, very constrained initial state that we know very well to a universe at the present day that is so complex and contains galaxies and stars and black holes and planets and you and me, that not even all the books in all of human libraries could even begin to describe the state that the universe is currently in. So somehow we went from relatively simple to extremely, extremely complex. And astronomers are interested in how that process happened. Now, we can observe this moment of recombination observationally with satellites that look at the cosmic microwave background radiation. That is kind of this radiation that's coming from that afterglow of the Big Bang, the moment it became transparent. But we also could look out from the present day at the local universe in this section of the history of the universe. And prior to James Webb, we couldn't see really much further than a redshift of 10. So we couldn't really get into this, observationally get into this era when stuff was first forming. So we can kind of have observational measurements here and here, but in the middle, there really isn't, there wasn't a way to look at that for so long. And now with JWST, we're going to start to be able to actually observe things at that time, which is really amazing. I've seen papers that claim to have looked at objects at a redshift of 20, which would just be incredible. I gave a talk in my class in the spring where I talked about objects at a redshift of 20, and my professor told me that I basically need to contextualize that language of redshift 20 and explain it to the audience, because we would never observe something at such a high redshift and nobody understood what I was talking about, and I would have to really work to get the audience to even care about my research. And now just a couple months later, I'm seeing papers every day that say redshift 20. So it's a kind of an exciting time to be an astronomer and somebody working in this field. So we went from very smooth to complex galaxies somehow. And now I'm going to describe kind of that process of how we get from a smooth plasma to things like galaxies and humans in a kind of a cartoon fashion. So like I said, in the beginning, the universe was extremely hot. It was compact into this small space, and it was very homogeneous overall. This is a picture of that Cmb radiation that was observed with the Planck satellite. So this is kind of that earliest time. And you can see that there's just small fluctuations. This is highly, the contrast on this is highly enlarged. So really, the fluctuations on this map are temperature, but two regions that are next to each other are not that different in temperature. It's a very small fraction of difference. Really, it was very smooth, but then over time, it expanded and cooled. So that's kind of our initial state. And now what I'm going to do is zoom in on this moment right before recombination into the plasma. And it might have looked something like this, right? We have some particles floating around, right? Maybe an electron, a proton, things like that. And they're stuck in this hot plasma. All of my little yellow arrows are supposed to represent photons that are whizzing around in the plasma, bumping into things. And so these normal matter particles interact with that light. And so they're kind of trapped in this plasma until that moment of recombination. So just to illustrate this, what if the electron wants to move closer to the proton or another particle? It can move over, but then it will run into these photons here and get pushed back. So if matter wants to start clumping up into some sort of object, it can't really, because of this electromagnetic interaction between the photons and the ordinary matter particles. So that's why the universe stayed so smooth for so long. But that's just ordinary matter. So at the same time, there was also dark matter in the universe. And we said there was much more dark matter than ordinary matter. So if I replace these two particles with dark matter particles instead of normal matter particles, the dark matter doesn't interact at all with light. So it can move freely through this plasma and do whatever it wants. And it interacts gravitationally. We know that dark matter experiences gravity. So these two dark matter particles might be gravitationally pulled towards each other by the force of gravity. But they can just move right towards each other because they're not stuck in the plasma. So dark matter didn't interact with light at all, and it could start to clump up before the normal matter could. So then the more matter that starts to clump, the higher the gravitational pull of those regions that are more dense. And so what you start to get is clumps of dark matter forming. And then here I'm zooming out. We now have regions of more dense dark matter, whereas the normal matter is still the smooth thing. So I'm representing the pink as clumps of dark matter, and the yellow is supposed to show you kind of the smooth plasma of ordinary matter and radiation. And if I look at just sort of a section of this with two clumps of dark matter, and I just plot in a cartoon fashion the density as a function of distance going along, I see that there are two peaks of dark matter density. So these peaks are regions where the dark matter is dense, but the normal matter, the gas, it's just pretty underdense. It's not doing anything crazy before recombination. So it looks like this. But then recombination happens, and the matter is no longer trapped in the plasma. So now it can start to clump together, and it's naturally going to clump in regions where there are already these huge clumps of dark matter. So the normal matter is just sort of falling into the dark matter halos. So we call clumps of dark matter frequently halos, and I'll be using that language throughout the talk. The normal matter is falling into dark matter halos. And when I look at my plot, I see that the density of the gas is increasing in the same places that the dark matter density was peaking. And eventually, the gas totally falls into the dark matter, and you end up with a dense clump of gas inside a larger dark matter halo. So that's kind of our standard picture of how this works. And I see a question in the chat. Can dark matter particles bump into and stick to each other? That's a good question. I'm not an expert on different theories of dark matter particle physics. There's many, I guess, ideas for what these actual particles might be like and how they can interact with each other. The only thing we need to assume for the purposes of forming structures is that it doesn't do anything when it hits a photon, and it feels the force of gravity from other objects in the universe that have mass. So maybe the dark matter particles are there's many different types of them, and they behave like all the different types of normal matter that are out there. I don't really know what the preferred theory currently is. There's people that are specializing in looking at these interactions between dark matter particles. But for our purposes, all we need to know is they feel gravity, but they don't feel electromagnetism. So yeah, that's definitely a cool question. I would like to know all of the ways that dark matter particles interact for sure. Okay, so our cartoon picture is that there's a big pile of gas inside a dark matter halo. And in lambda CDM structure formation, the way that we understand this is that those are the things that turn into galaxies. So poof, I have made my gas turn into nice little galaxies sitting in dark matter halos. Of course, it's much more complex than that. And I found a really beautiful simulation that shows this. Let's see if it will play. Give it some time. Oh, here it goes. Okay. So here we have gas that is clumping together and forming a galaxy in a simulation. And so you can see it all starts condensing and coming in. And you don't really need to know too much about this. I just want to show that once you have a clump of gas, it begins to form very complex structures like galaxies. And this is a long video, but it's very beautiful. I will skip to the part where it becomes starts looking like something you might recognize as a galaxy. maybe it's in here. Yeah, so here we're going to see it's formed this kind of spiral shape. It's really starting to look like a structure we could observe out in the universe. And as it's condensing, there's stars forming, so it starts to light up. And this is just the typical way that we understand that this smooth plasma turns into actual galaxies. And I want to point out that this is a highly successful theory. And it describes our universe very well at large scales. And to illustrate this, I have two pictures, and one is a Hubble Deep Field image, and one is a simulation image. And so I feel that some of you have probably seen this side by side before, but just think to yourself, if you could figure out which one of these is real and which one of these is a simulation, assuming lambda CDM. So they put the conditions of lambda CDM and the physics that we know, and they run the simulation and they see what we would observe with Hubble, and they came up with one of the images. Okay. The time scale of the galaxy formation simulation. I see a question in the chat. Off the top of my head, I'm not sure. It was the first one that came up when I searched galaxy formation simulation. So I think it was a very long time scale. It does not happen that fast. So over millions and billions of years, it does that.
So Claire, is one of these pictures the Hubble Deep Field?
One of these is, yeah, with Hubble, and the other one is a simulation.
Oh.
And I think probably everybody has had enough time to maybe make their choice. I'm going to reveal the answer, and you can see if you were right. This is a Hubble Deep Field image, and this one is the Illustris simulation. And you can see how well lambda CDM is doing. It really constructs a universe that looks very similar to ours. If you're wondering, the way that you can tell before I revealed is that the Hubble has these stars in the foreground that have diffraction spikes on them, whereas the simulation doesn't have any foreground stars in the way. So if somebody ever asks you this question again, you can tell here there's a little star and here there's a star. But really, it's quite impressive that they have been able to follow this process and basically create a universe that looks like ours. So a highly successful theory, but it's only successful at these very large scales. On small scales, there are some sort of thorns in the side of the lambda CDM theory that keep presenting problems. One example of those is globular clusters. I'm sure you have all seen them with telescopes. They're incredibly beautiful systems of many, many stars. So these groups of stars, and astronomers have figured out that they are very old systems, maybe older than the galaxy itself, and they have little to no dark matter in them. And this is a bit strange because we just said that in lambda CDM, the way that things form is that first dark matter sort of clumps up, and then the normal matter falls in. So it's a bit difficult to form a system that doesn't really have any dark matter. So a lot of work has gone into proposing different mechanisms that you could form these and maybe strip away their dark matter somehow. But I'd say there's not really a consensus in the community right now of a surefire way that we could just create globular clusters with lambda CDM. And additionally, there are these dwarf galaxies that also present problems or tension for the lambda CDM theory. These are just small galaxies, maybe like satellites of the Milky Way or other galaxies. You know, they're not as big as like the Milky Way or Andromeda. And a bunch of problems have sort of come up where there's tension between observation and theory. And so, oh, I see there's a question. A dark matter black hole at the center of globulars. I think you are suggesting a possible way to explain the observations of globular clusters, which, yeah, like I said, there's a lot of potential observational ways to resolve this, and like theoretical ways to resolve this, but nothing that everybody agrees on. And then, okay, I see another question. How does each mass enough to make a star? So how do you get enough mass to form a star out of a cloud of gas is maybe what this question is asking. Basically, to form stars to the first level of approximation, you need to have gravity win over the pressure in the gas. So gas inherently has some pressure. You probably remember like the ideal gas law from your chemistry classes or physics classes. And so if you just have gas floating around and it doesn't feel that much gravitation, there's not much mass, it doesn't necessarily collapse and start forming a star. You need to have a large mass of gas and it needs to cool down enough that it gets, that the force of gravity can win in the fight against that outward pressure from the gas itself. So you need to get dense enough that a star can form. And a star forms when there's like an ignition of fusion in the core of the star. So basically, to a first level of approximation, you can balance the pressure term from the gas against the force of gravity inward, and find a mass scale at which things can start to collapse down and form a star. So I hope that's kind of what you were asking. I'm not as much of an expert in the star formation aspect of this. Yeah, so these dwarf galaxies are kind of another problem. I'm not going to go into all of these, what these problems mean, but I'll just say that there continue to be tensions between observation and theory, specifically with the amount of dark matter in these different types of objects, not correlating to what you would expect from typical structure formation in lambda CDM. And so this is just a summary. Here are the objects we want to explain. On the x-axis, we have their size, and on the y-axis, we have their absolute visual magnitude going. So that's just a measure of how bright this thing is, going from dim to bright. The globular clusters in the galaxy are in the pink circle, and then the blue is different faint dwarf galaxies near the Milky Way, Andromeda, and our local group. So people love to work on this question, and a lot of times people will say maybe there's some new physics involved, something that we didn't consider in our original formulation of the universe, right? Those ingredients we talked about at the beginning. Just yesterday, I saw a paper that was observing some small dwarf galaxies, saying that they lack dark matter, and then saying, concluding that this is incompatible with lambda CDM expectations and consistent with a totally different theory of gravity. So people like to say, well, we need to throw out all of lambda CDM because these observations are not matching what we would predict from our typical theory. However, I am today going to present an update to lambda CDM that will hopefully fix some of these problems. Oh yeah, okay, I see. That wasn't, there's something in the chat. Oh, okay, cool, not a question. So yeah, we're going to hopefully save lambda CDM by providing this supersonic update. And here's what I mean by that. About a decade ago, it was pointed out that there was a term that had been neglected. So the supersonic speed of normal matter in the early universe had been forgotten. I say forgotten, it had been, in order to simplify the equations, you know, because we are very lazy in theoretical physics, they had just gotten rid of that term and not included it when they were doing calculations. But really, what that term was describing was the fact that normal matter was streaming past the dark matter in those early times at supersonic speeds. And to remind you what supersonic means, just means you're traveling faster than the speed of sound. So I put a picture of a military jet breaking the sound barrier. That means you're traveling at least Mach 1. So there's this Mach number that describes how supersonic you are. I was just watching the new Top Gun movie, and he was in a jet that was going at Mach like 9 or something crazy like that. So you can do this in Earth's atmosphere by traveling faster than the speed of sound in the atmosphere. In this case, you are traveling faster than the speed of sound of the early universe. So on average, the normal matter was traveling at Mach 5, so 5 times the speed of sound. And that's quite a high speed. And it means that you can't exactly throw out that term in the theory, because it's quite a high, like a large magnitude. So it's not just a small term that can be neglected. And I see another question. This is a good question. Aren't dwarf galaxies just leftover bits of galaxy collisions? Were there dwarf galaxies in the very early universe? This is a great question. So there's lots of different types of objects in the universe. And our model of how structures form currently is called hierarchical structure formation, which means small things form first, and then they merge together to make bigger things. So definitely there was dwarf-sized galaxy things in the very early universe. The problem here is that certain types of dwarf, so there can be dwarf galaxies from galaxy collisions, there can be all kinds of things that generate different types of galaxies. The problem here is that there's certain dwarf galaxies, especially galaxies called ultra faint or dark satellite galaxies, also these globular clusters that just don't seem to observationally fit with anything we can create theoretically in a simulation. Okay. All right, so the supersonic velocity turns out to change our picture of structure formation. And I'm going to show you, going back to that cartoon I was showing, how this works. So, okay, so I was saying the normal matter is traveling at a supersonic speed. And I'm returning to this cartoon with the clumps of dark matter in the baryons, or normal matter, the plasma of this normal matter. And here, the normal matter is now moving at a supersonic speed relative to these clumps of dark matter. Okay, so when the matter starts to fall into these dark, gravitationally attractive dark matter clumps, it still tries to fall in, but it misses. So it's ending up with these overdensities still, but they're offset from the dark matter. And you can see it here in my plot. Remember, they used to be aligned, right? There was 2 gas peaks and there was 2 dark matter peaks, and they were all lined up. Now the gas peaks are slightly shifted to the side because the dark matter is offset from the normal matter. And so we can still go through our process of structure formation, right? The gas is collapsing, but we end up with an actual physical offset between dark matter and ordinary matter. And so at the end of the day, the 2 peaks are next to each other, not on top of each other. And I will add that this effect is only relevant at very small scales. So something the size of the Milky Way is relatively unaffected. The offset is so small compared to how big it is that you basically have normal lambda CDM structure formation proceed as normal. But for something the size of like 10 to the 5th solar masses, or to 10 to the 8th or 9th or so solar masses, this actually can be a very significant effect. And so I just want to remind you that a classical galaxy is surrounded by a huge halo of dark matter, right? Because the gas condensed, it formed stars, and over time it became a galaxy. You get something like this, right? A galaxy inside a dark matter halo, and it's sitting in the very center of that halo. But what we are predicting is that some smaller sized objects, the ones that are most affected by this velocity, should have anomalous or even no dark matter halo at all, right? So this object on the right has been offset from its dark matter, and this object on the left is totally outside of the dark matter, right? And so that dark matter can just be totally separate, and the gas ends up as its own object, which is really unusual. And these objects have names that were coined. Some of the collaborators a few years back called the gas objects that totally don't have very much dark matter at all. They called those supersonically induced gas objects, or SBAUs. And then in a paper that I'm currently working on when I'm not giving public talks is we're coining the other structures here where they're offset. We're calling them dark matter ghost. These two types of objects are predicted by this theory. So, and the dark matter ghost stands for dark matter and gas halo offset by streaming. So these two types of objects are expected to exist in regions of the early universe where there was a very high supersonic velocity. And to summarize, so far, just so we're all on the same page, we know there are problems with lambda CDM at small scales. We also know that there is a new effect, the velocity, that comes into play at small scales at early times. And so this generates new classes of objects, right? The SBAUs and the dark matter ghosts that have anomalous properties, at least early on. So we need to understand more about these theoretically predicted structures to understand what their role is later on. And my advisor made a really great analogy the other day to fossil hunting that I really liked. So this is how I have been understanding this. It's kind of like being a paleontologist. So using physics alone, we predicted the existence of objects at early times. And this is like if you're a fossil hunter, right? You find some weird skeleton from millions of years ago. But then you look out at the animal kingdom today and you see a huge range of life and diversity. And you wonder, okay, this creature was living millions of years ago. That species must have evolved for millennia. What became of it, right? Did it evolve into something, was it a dinosaur that became a chicken? Did it just totally go extinct? What happened? And you have to fill in the missing steps. We're kind of doing the same thing. Structures, we've found that there's some strange types of structures that must have existed just based on physics alone in the early universe. But this is in an era, like I said, that was never observed. This is in those cosmological dark ages that were previously unobservable before the James Webb Space Telescope launched. So the strange structures existed, then billions of years passed, and now we observe a diversity of different types of objects. We can see lots of galaxies of different shapes and sizes, and we wonder what became of those first early weird objects. Did they turn into something that we currently see? Did they merge with other objects? Did they become something of their own that we haven't observed yet? Are they unobservable? Who knows, right? And so the obvious thing to do is to try to fill in this history between the strange structures at the beginning and the current day. So there's two ways to do this: theory and observation, the classic two pieces of astronomy that have to work together. So using observation, we could observe the early universe and its history between then and now. And I put a big check mark next to that because, yeah, all right, we're going to do that. We've got a big telescope that just went up, and we're going to be doing lots and lots of amazing science looking at those early galaxies, right? Two of its science goals, the motivations for this mission were to look at the early universe and the history of galaxies. So then using theory, we can use analysis, math, and numerical simulations to understand what we are looking at, right? So we get a photo from James Webb like this. We can zoom in and see lots of little tiny spread smudges from a very early time. But we need to know what does it all mean, right? We need to have context for those observations. So here we are at the Supersonic Project. Our job is to understand these supersonically formed objects and try to connect them, make predictions that observers could test. So at UCLA, there's me, Claire Williams, and then also William and Yo just graduated recently. And then our advisor is Smadar Naus, plus all of these people around the world who have been helping us out with this project. So I just wanted to shout out the Supersonic collaboration because, like I said, I'm a first year. I just finished my first year, and these people have been doing this since I was in high school. So really, they've been doing a cool job, and I'm so excited to be joining on this project. So yeah, huge shout out to them. And William has a paper that's coming out soon, so keep an eye out for that. Okay, so just going to our methods, like I said, we use cosmological simulations. For those who are not, haven't really thought about this too much, right? We can make a computer simulate the conditions of the early universe, and we tell it to take that supersonic velocity into account. So on the right-hand side, I'm showing just basically a screenshot from a section of one of my simulations that shows the density of gas I think this is at a redshift of 20. And then in the same region of space, I've overplotted dark matter particles in the simulation as red dots. So you can see that there is a complex interaction of gas and dark matter. And you can probably also see why we need a simulation to do this, because I do not want to be working out all of the equations of every single one of the millions of particles in this box. And using a computer, we can do a much better job than any one graduate student could ever do. So we're using simulations to discover these objects in a pretend version of the universe. And then I also just want to say I do a lot of math under the hood. This is a picture of my desk 2 days ago. If there's any young people that are watching that are interested in getting into theoretical physics, if you are a person that likes math and likes doing coding, that's basically my whole day, every single day. So it's really fun, and it's a good job. I like that I get paid to do this. So yeah, that's our method. Here is just an example. I'm just going to show you a couple of examples of how we find these objects. This is a SEGO that I found in the simulation. It's, again, we have the gas density on this plot on the right here. And this little white outline shows you where the algorithm found it. So it's kind of this long shape. It's just like a big ellipse of gas. And then if I plot the dark matter in that same region, what I see is that there's like very little dark matter in that area. So I have an object that formed with gas, but it's offset from this dark matter halo right here. So it's living outside of the overdensity of dark matter that we can see up here. So that's a SEGO. Yeah, so it contains gas, but very little dark matter. I also am showing here a dark matter ghost. The same idea, except this yellow circle is the radius of the dark matter part of the ghost. And the orange line shows you where the majority of the gas component is. And you can see that the two are offset. They're not in the same location like a normal galaxy would be. And then here's just more pretty pictures from the simulations. This is a SEGO here, and then 2 DM ghosts. And they're all just look very different from the normal type of structure that we find in Lambda CDM. And so just the last cool result I wanted to show you is that we have some promising results that actually suggest that there may be a link between these supersonic objects and nearby objects that we see in our universe. So I'm going back to this plot where we had the size of objects on the x-axis and the brightness of the objects on the y-axis. Here were the globular clusters, and then here were the different faint dwarf galaxies. Yo had written a paper where he basically created the same plot, but instead of these classes of objects, he just plotted the dark matter ghosts as dots and the CGOs as stars. So so this is their size, this is their predicted brightness if they formed stars and lived to today. And what you can see is that the CGOs seem to be occupying a similar region of parameter space as the globular clusters. And the dark matter ghosts seem to be living in that region of parameter space where the faint galaxies were. So there's sort of this tantalizing idea that potentially globular clusters could be a formation channel for, or CGOs could be a formation channel for globular clusters, and the dark matter ghost could be a formation channel for some type of dwarf galaxy. But this needs a lot more investigation. This is just some properties of these objects that we have found so far. Just the ways in which they are sort of different from normal objects that form in regions where there's no relative velocity. They're less spherical, so they're more elongated. They have higher angular momentum. There's obviously a mismatch and offset between the dark matter and the normal matter. And sometimes there's even a mismatch between the angular momentum of the dark matter and the angular momentum of the ordinary matter. They also, in the paper I'm working on, we're showing that they have anomalous rotation curves and density profiles. So these are all sort of predictions that will help to compare objects observed with the simulated objects, right? So we want to try to pick out these observable quantities that could potentially be compared with an observation of an actual system. So that's what we're working on, but the whole project is very much in the early stages and there's so much work to do. So great for a beginning student in the field. There's a lot, so lots to work on, but nothing extremely conclusive to say decisively what is happening here, but definitely very tantalizing and exciting. So that's all I had for tonight. Here are some sources of funding and also my website if you're curious. After I write this paper, I'm going to update it with sort of the more recent results, but I don't want to do that before I've published. And then lastly, I just wanted to give a plug for the UCLA Planetarium. Since you are all astro enthusiasts, we are a totally graduate-run planetarium, and I'm one of the coordinators of it. We do weekly shows on Wednesday nights during the academic year, and we also offer private shows for educational groups. So if you find yourself in the Los Angeles area, I highly recommend. So thanks so much for listening, and I would be happy to answer any questions that you have.
Claire Williams, everybody. Do you also have an observatory down there?
We have some public like small telescopes. We don't have like
okay, like
a research telescope. The as you know, the University of California is involved in the Keck telescope. So a lot of the people in my department are doing remote observing on Keck. Or other telescopes around the world. But we do have a lot of, actually it's an undergraduate event. The undergraduate astronomy club here does like night sky showings with the small telescopes. So I think they have a little collection of small telescopes that they show to the public sometimes after the planetarium shows. So
whereabouts at UCLA is the planetarium?
It's on the roof of the Math Sciences building.
Is that Knudsen Hall?
No. So Knudsen and the physics and astronomy buildings are where our department is, but the planetarium was built on the place where the old astronomy department was located, which is now called the Math Sciences building. So I recommend going to, if you're actually visiting, I recommend going to our website and finding the directions to visit it, because you have to find the building and then go up like 5 flights of stairs, and there's a cranky elevator you can use as well, but it's a little, it's a little complicated.
Did we get a question on the screen? It vanished.
I see a question from Tom.
Okay.
Any thoughts on black holes and other masses forming during the Big Bang due to densities? Yeah, I guess I have thoughts. I don't have like a definitive professional opinion on the subject. That would be very cool. I think you're referring to primordial black holes. So if there's anybody who is not familiar with that term watching this, there's a theory that there could be tiny little black holes that are formed early in the universe, and most black holes that we know about, or I guess I should say all the black holes that we know about, are at least the size of a star. So we know that stars can collapse and form black holes. We also know there's supermassive black holes, but this theory predicts that there could be tiny little black holes in the universe, which would be very, I guess, exciting and maybe a little scary. There's a physicist who is a few years above me in the graduate program at UCLA, and he has a theory that primordial black holes, tiny little black holes, could end up in the galactic center, where they would undergo a lot of collisions with neutron stars. So these are very dense remnants of old stars, and they could get slowed down and eventually fall to the center of a neutron star. And then this is a predicted object that would be one of the G objects. So there's these mysterious G objects at the galactic center that nobody, there was a lot of debate whether they're a cloud of gas or a weird shaped star, all kinds of things. And I thought it was very interesting to see them even predicted to be primordial black holes at the center of neutron stars. So they seem to show up everywhere.
Chuck or Pat, do you have a question? Well, I have a quick one. My understanding was dark matter was first theorized or proposed because they needed something extra to keep the galaxies whole from flying apart. And yet they have discovered galaxies, have they not, that somehow they deem they don't have any dark matter? Why aren't they flying apart in the middle of space?
That's a great question. Yeah, if there's, I think one of the problems for, like, one of the reasons, like, for example, globular clusters are such a problem is it's hard to get anything to form in the first place without dark matter, providing that gravitational potential for things to collapse into. Right, I said that in order to form stars, you have to overcome this outward pressure of gas. And so that was a problem, because if you have a globular cluster, how did it even form any of the stars that are in it without being at the center of that dark matter halo to be able to collapse and form stars? This stream velocity effect tells us that for some objects, you can have them collapse because of the influence of that dark matter, but not wind up in the center of the dark matter. So even though they have no dark matter, they would never have collapsed gravitationally in the first place if there wasn't that potential, the gravitational potential of the dark matter. Now, as far as how they don't fly apart, as in like just totally evaporate due to like a dynamical process, I'm not sure. And I know that there's this idea that a lot of globular clusters probably already did evaporate. So yeah, it's a good question.
Thank you. You got to it. What, another question on the
Oh, I
screen?
see. And they don't have organized disk type rotation. Yeah. Yeah, like I said, one cool thing that we're finding is that our objects in the simulations have anomalous rotation properties. So that's kind of exciting.
Yeah, my point was that the little dwarf galaxies don't have a nice organized disk and set of rotations like spirals do. And the way this dark matter problem was noticed was in spiral galaxies where you had the rotation of the disk.
Small dwarf galaxies like our local group?
No, we're not dwarf galaxies, but like the large and small clouds of Magellan.
That's what I meant, in our local
Yeah.
group.
Yeah.
And they're not redshifted because they're coming at us, aren't they, or orbiting us?
Well, that's something totally different, but yeah.
I know, but we all know there's matter versus antimatter, but matter seems to dominate. I don't suppose they've spotted either with the Webb or anything else galaxies made of antimatter, in which case would they have anti-dark matter?
That'd be pretty tricky to tell that it's antimatter versus matter.
Maybe you wouldn't be able to see them. I don't know. Interesting. Well, very fascinating stuff there, Claire. How do we read your paper? Is that possible online when it comes out?
Yeah, it'll be posted on the archive. First I need to finish the draft, and then I just send it to my collaborators, and then they need to give me lots of feedback, and then I need to send it to a journal, and then they need to give me, so it's going to be a long time. But I'll post it for sure on my website.
Okay.
All right. Well,
thanks for tonight's talk. It's been very interesting. There's a couple of epiphanies in there I never realized. Excellent.
Yeah, I hope you guys got a little excited about the theoretical side of things. I know you are passionate observers. Well, there's lots of even us theorists get very excited about new telescopes and the prospect of new data. So yeah, lots to look forward to in the community.
And you have a good scope yourself, I would assume. Hey, thank you very much on behalf of the club. And Jerry, you want to close things out next month? It's the Webb with our own Chrissy Cook and Dr. Rocio. So Jerry Wilson, our president, would you close the meeting out? And thank you again for all attending.
Okay. I don't think we have any more announcements, Chrissy. Nothing? Okay, well then we'll see you all first.
Top player, great job. That was fantastic.
See you all first Friday of next month.
All right. And Monday at 11. Thank you.
It was great to meet you. Thanks so much.